Okay, so this is Chapter 15 homework set. We're going to start with the first problem. It says two pulleys are operated with the V-belt in three positions if the angular acceleration of shaft A is 6 radians per second squared, and the system is at rest. Determine the time for B to reach speed of 400 RPM at all three positions. There's a little diagram of it. So we have shaft A, shaft B, and the different positions on the belt. On the pulleys, I mean, for the belt. So what we can do is we can find the velocity of the belt using the right-hand rule. And the velocity of the belt is going to be the angular velocity times the radius. And that's, we're assuming that there's no slip here. If it slips, then we've got other problems. So there's that. Now we know that the angular velocity of A times the radius of A is going to be the same as the angular velocity of B times the radius of B. So it's going to be the same throughout the whole cycle. So what we can do, we can figure out the angular velocity of A if we get the angular acceleration of A times t, times the time. Subbing that into our equation, we will have the angular acceleration times t for the angular velocity of A. So we're going to sub that into this point right here. Doing so, it's going to give us the angular velocity of, angular acceleration times time times the radius of A equals the angular velocity of B times the radius of B. And rearranging for t, for time, we have the angular acceleration of B times the radius of B times the angular velocity of B times radius of B times the angular acceleration of A times the radius of A. So we know that the angular acceleration is 6 radians per second squared, and we know that it's well, I guess we're kind of assuming it's constant. We don't know it's constant. So for the angular velocity of B, we know we want it to reach 400 RPM. Now, RPM is revolutions per minute, 2 pi radians per revolution, and 1 minute has 60 seconds. So cycling that, or multiplying that through, we're going to have an angular velocity of B at 41.89 radians per second. That's what we want it to get to. So at point 1, we are going to have position 1, excuse me. We have a 2-inch, a 3-inch, and a 4-inch position. So at position 1, we're going to have 2 inches. We want that again. If we go up here, we have the angular velocity times radius. So we want it to get to 41.89 radians per second, and it's 2 inches in diameter. Diameter or radius? No, I believe it's the radius. I don't remember if the radius is 2 inches or if it was the diameter. But let's say it was 2 inches radius because that makes sense. Diameter screws us here. So we're going to sub into this equation angular acceleration times 4 inches, 4 inches for the radius of A. And that gives us a t1, or time to get to the first velocity requirement at position 1 at 3.49 seconds. Position 2, we know that's 3 inches. We are going to then switch on A to the second position here, the 3 inches. So we're going to have 41.89 radians per second times 3 inches, 6 radians per second squared times 3 inches. That's going to take us 6.98 seconds to get to the requirement. So, or the velocity requirement. Position 3. Position 3, we now have 4 inches for B and 3 inches for A. 2 inches for A, sorry. 2 inches is the inside one. That screwed me for a second. So 41.89 times 4, and then divide by 6 radians per second squared times 2. That gives us T3 of 13.96 seconds. Okay, so now we are going to the second problem. What we have here, let me see if I can adjust the camera a little better. Load is raised 20 feet by a hoist. Assuming gear A is at rest, accelerates uniformly to 120 RPM in 5 seconds and is constant 120 RPM after that. We have to determine the number of revolutions of gear A in raising the load and the time required to raise the load. This is a little diagram of it. So this pulley is actually attached to the inside diameter there, not the outside diameter. The inside diameter is 15 inches. The diameter of the entire pulley or gear is 18 inches, and that's what's attached to the A pulley, or the A gear. They're not pulleys, they're gears. So, what do we know? We know that the angular velocity, omega, of A, we want it to get to 120 RPM. It's going to be at 120 RPM. Multiplying that through by 2 pi radians per revolution, 1 minute per 6 seconds, we have 12.57 rads. So that's what gear A is accelerating and then continuing after it reaches that point. Accelerating to and then continuing that point. We know that omega is equal to angular acceleration times time. We adjust here to solve for angular acceleration. And we know we're assuming a uniform or linear acceleration. So what we'll do is we'll take our final omega, 12.57 rads, and we're going to divide through by the time requirement, which is 5 seconds. So that gives us an angular acceleration of 2.514 radians per second squared. Now, we know that the height of the load is at 20 feet. That's how much we'll want to raise it. That's 240 inches. So that means that as this travels 240 inches, this gear is going to have to turn at least 240 inches, right? Same with this thing. This one's going to be a little different, though, because it's attached to the outside diameter, so it's going to travel a little further than the inside diameter. The inside diameter has to travel 240 total inches, so it has to make a couple revolutions. So we know that one revolution would be, if we take the circumference of the gear, we know it's 2 pi r is the circumference of a circle. So for B, 2 pi times 15 is equal to 92.25 total inches. And we know A is 3 inches in diameter. It's a small little guy, so it's going to be 2 pi, 3 inches. It's going to be 18.85 inches per revolution traveled. So what we do now is we know we're going to travel this 240 inches. And we know it's going to be pulled up attached to B. So we're going to divide that by that, and that gives us our total amount of revolutions for B. So 240 divided by 92.5, that's going to be 2.6 revs of B. Now we know it's 2 pi rads per revolution. That gives us 16.5 radians of B. So now that's for the inside diameter of B. The gear is actually attached to the outside diameter. So gear B travels 18 inches times that radian. So it's rotating that many times, but it's going 18 inches in diameter. Or sorry, in the radius of it is 18 inches. So that's going to give us 294.24 inches is how much B, the entire gear of B, travels. If we divide that 2 pi r of A, and that gives us this distance, this total distance